Alright, this chapter is on organic chemistry, and we're covering this in general college chemistry 2 to prepare you for organic chemistry, which may be the next chemistry class that you take. And if it's not the last, if you're not going to take organic chemistry, it's still important that you understand some of the basics of organic chemistry. Even if you're thinking like something like engineering, maybe civil engineering, maybe you're thinking that you'll build bridges in the future or design bridges. In the future, maybe the bridges aren't going to be made of concrete, but of some type of carbon fiber or carbon nanotubes or something like that. So I think it's important that everybody have a little bit of organic chemistry. Most of your pharmaceuticals, polymers, plastics, they're all based on carbon. So a small foundation of how carbon behaves and why it's so important and that it has its own chemistry by itself, it's worth an introductory lesson on that. So let's look at the topics. We're only going to cover the first 4 sections. We're not going to get into the organic reactions, organic polymers in this class. Again, what I'm trying to do is to give you exposure to organic chemistry so that hopefully you'll take the organic class and you'll start the class with a small foundation in organic chemistry, like it won't be totally unknown to you. So why is carbon different? Organic compounds representing organic molecules and isomerism. And this is going to draw from Gen Chem 1 the sections on Lewis structures, geometries, and also a little bit of intermolecular forces. So we'll see all of those here. So why is carbon different? So what I'd like you to think about before we move on, can you draw a Lewis structure for carbon and determine how many bonds does carbon want to form and why does it want to form that many bonds? So carbon is different because it can form 4 bonds, and those bonds can either be sigma bonds, pi bonds, or a combination of both. So I didn't talk about this in Gen Chem 1, and I think it's worth talking about at this point. And so what is a sigma bond and what is a pi bond? And a sigma bond is a bond that is in line with the nuclei, and it's so we generally, that's what you're probably most familiar with, is a single bond between 2 elements. Generally is a sigma bond if we're definitely talking about covalent compounds. Pi bonds are bonds that are off axis. They are not on the primary axis, but above and below the primary axis. And there's a cloud of electrons that are above the nuclei or below the nuclei or to the side of the nuclei. They're not in the direct path of the nuclei. So we can see there are different orientations here. We have methane. Can you tell me what the geometry is for methane there? So you should be able to look at that and say, well, this is an AB4 or AX4, which means 4 bonding groups coming off the central atom, and that's a tetrahedral electron domain geometry and a tetrahedral molecular geometry. And again, if those sound new to you, those terms, I would refer you back to chapter 9 in the Birch book to read about molecular geometries. Then we have a trigonal planar molecular geometry for formaldehyde in the middle there. And there are 3 sigma bonds, 3 bonds that are directly in line with the nuclei. But we also introduce a pi bond, and that pi bond is what creates the double bond that you see between the carbon in black and the oxygen in red. So that pi bond would be off axis, and that's formaldehyde. And then we definitely did the Lewis structure. I think everybody does the Lewis structure of carbon dioxide in Gen Chem 1. And you know there's double bonds between the carbon and the oxygen. And so in this case, there's two sigma bonds, and then there are two pi bonds. And that creates the double bonds between carbon and oxygen. So to give you an illustration of what a pi bond looks like, let's look at this. So it says carbon's small atomic radius allows the atoms to approach one another closely. That's really important to remember too. Carbon is in period 2. It's a very small atom, and it allows the atoms of carbon to get very close, which allows an overlap of these pi bonds, which are shown in purple here, above and below the axis. So we don't see that with silicon. The silicon, by adding another shell to silicon, we're separating the atoms far enough that we don't get that pi bond interaction at normal energy. We still get a p bond or a hybridization here. So the green, let's talk about this. This is something to review from, again, chapter 9. You know about s orbitals and p orbitals, and you know the p orbitals, you would have a pxy and a pxz, and you have a px, you have a py, and you have a pz. And so let me just draw that for you here. So we learned in chapter 9 that the p orbitals are directional, and that they are on the axis. And so let me let's see, all right, so the p orbitals, dumbbell shape. There's one here, there's one down, and that's like on the z-axis. Let's call this the z-axis here. And then we have one along, I'll call it the x-axis. So that would be like this. And then there's one coming out of the board like that. But you notice that these green ones, they're 120 degrees from each other. And that's a hybridization. That's a hybridization called an sp2 hybridization. So again, you'll see that trigonal planar type arrangement. They're 120 degrees from each other and they're flat. And so the only way we can get this 120 degrees is by taking an s orbital and blending it with two p orbitals to give us more bonding sites. So the other thing I want to point out here is, so if you haven't heard about hybridization, again, you're going to need to read chapter 11, and there's a section in chapter 11 on hybridization of orbitals where we blend s and p. In my class, what I teach is if it's sp2, then we're going to have a trigonal planar. If it's sp3, the electron domain is going to be tetrahedral. If it's sp3d, it's a trigonal bipyramidal, and if it's sp3d2, then we have octahedral type electron domain geometry. So if this is all new to you, if you haven't heard this, if you have SP and linear, if you haven't had this before, you're going to have to read that section in chapter 11 to understand hybridization. And pretty much what it is, I mean, I'll do a little bit of it here. So you know carbon, if you look at its outer shell, it's got the 2s electrons, and then it's got 2 electrons in the 2p. And so if I blend an s with these 2 p's, then I have sp2, and I have 2 bonding sites here, and then we can have a shared one here. So there could be up to 3 bonds coming off of the carbon. If I blend an s with all 3 p's, then I get, again, 3 new orbitals. They're all the same energy, and each one has one of the carbon electrons. So there's 4 bonding sites, and that allows something like hydrogen to bond at each one of these sites, and we get something like methane to tetrahedral. Anything beyond tetrahedral, we're going to have to look at taking an element that's in period 3 that has unfilled d orbitals and blending those together. So that's what we're getting at. So here they want to talk about, in addition to carbon atoms, there's this hybridization approach, and that they're closely, these bonds are close enough, whether it's unhybridized or hybridized, to create a strong bond. So carbon's valence electrons are in the second shell where there are no d orbitals, and so we have ethane and we have disilane, and so the disilane, you can see that bond is much longer here because you don't have that overlap of the pi bonding, the orbitals, so that they can overlap there. But again, the advantage is that the distance between these 2 carbon atoms, because carbon's got 1 less shell, allows overlap of the non-axis orbitals. So here, what we want to talk about is you got to speak the language of organic chemistry, and that is you have to talk about primary, secondary, and tertiary carbons. So it says these attributes, you can form chains with carbons, either straight, branched, or cyclic. They can be single, double, or triple bonds. And carbon's formation of the chain is called catenation. So you need to know the word catenation, where carbon can form bond after bond to form a chain. Okay, on this chain, you can see that this carbon is attached to 4 other carbons. So that's a 4-degree carbon. You can have a carbon that's attached to 3 other carbons at the 3rd-degree carbon, or you can have a carbon that's only attached to 2 other carbons, which is a 2nd-degree carbon. So the degree tells you what's going on with each carbon. A 4-degree carbon is going to have 4 carbons attached to it. 3rd degree is going to have 3 carbons and then something else attached to it. The 2nd degree only has 2 carbons. So organic chemistry, we're looking at organic compounds also form bonds that are cyclical. And the simplest of these carbons where we're going to have pi bonding, which you see here, which is also resonance in that 1 second it's here, or well, I shouldn't say that. It's resonance, which means that there are bonds in the pi. Again, you got the axis bond, and then you have the bonds above and below called the pi bonds. And they're actually all around this. There's pi bonding all around this. And this group of compounds is called, they're cyclical compounds, but specifically these type of compounds where the electrons can freely go around these pi bonds, they're called aromatic compounds. So the way we show aromaticity is you can show the bonds like this. The shorthand way is to draw it like this and then just put a circle in it like that to say that this is not cyclohexane, but it's actually benzene. So cyclohexane looks like this too, but it doesn't have the pi bonding where the electrons can freely move around, and therefore we have cyclohexane and then we have benzene. Benzene has this resonance that creates some stability, and it also affects the chemical and physical properties. From the benzene ring, we can then add constituents to it. And when we add the hydroxy group to benzene, it's called a phenol or a phenol. If we add this particular group, which is an aldehyde, and you go, how do you know it's an aldehyde? Well, we'll talk about that. But if you have a carbon double bonded here, and then off of the carbon is a hydrogen, those are called aldehydes, all right? And so this is cinnamic aldehyde, or cinnamaldehyde is another name for it. But it's also attached to this benzene ring. So the simplest compounds that we work with in organic chemistry is called aliphatic compounds. So aliphatic are chain compounds. They do not contain a ring structure. So they're a chain of carbon atoms. And so these are the simplest ones. And so we have names for these. This is ethanol for two carbon chain. If it was a 4-carbon chain, it would be called butane. And there would be hydrogens where this oxygen hydroxy group are. But because there's a double bonded oxygen here and a hydroxy group here, this is an acid. This is a type of carboxylic acid. So we call this butyric acid. The but stands for the 4-carbon chain, and then this hydrogen here is acidic. This is again a carboxylic acid. This group here. And so that's why it's called butyric acid. Here we got the chain is 3 long, 3 carbons long, and we could call it propone, but it's a ketone. Why is it a ketone? Well, again, you have the double bonded carbon here, but instead of having just a hydrogen on one side and like an aldehyde, you have a carbon on either side of the double bonded carbon oxygen. That makes it a ketone, and particularly this ketone is called acetone. So you've heard of acetone in the lab. That's the most common name for it, but it could also be called propone. So classes of organic compounds, naming organic compounds. All right, so there's a huge variety of organic compounds. Each has their own characteristic properties. And so what we're looking at is carbon has the ability to form chains. So that's something we don't see a lot of in other elements. And these chains, when we add other elements to the carbon and hydrogen, it really changes the properties. And then we have functional groups like the carboxyl group or the double bonded oxygen. These functional groups change the properties as well. And then the last thing that's neat about carbon, it can form single, double, or triple bonds. So it can form multiple bonds. It's not just single bonds only like a lot of other compounds. So I want you to know these functional groups because it's important that you can identify the different classes of organic compounds. Now, we're not going to do them all. Take organic chemistry, you will definitely look at a lot more than what we're going to cover in this class. But there's some that's really important, and they come up over and over again. I don't care if you major in chemistry or not. You hear these compounds come up. Like if you ever painted your house with maybe an oil-based paint, it's probably got toluene in it, all right? It's a common compound in oil-based paints. So the first one we've really already talked about, the thing that flags it for you here is the carbon double bonded to an oxygen. And then you look at what's next to these two carbons, and there's a carbon on this side and a carbon on this side. And so that tells you it's in the form of a class of compounds called ketones. And again, this is called acetone. And what I want you to be able to do is a Lewis structure, and then I want you to be able to do the geometry. If you look at the, let me erase that and kind of show you what's going on here. All right, so if we go to that, let's say if I change this to black here. This carbon here is AX4 or AB4 if you like that better, but it's 4 bonding groups coming off the central atom. So if it's AX4, it's tetrahedral. And then this is identical, so that's tetrahedral. And then the carbon in the middle has only got 3 bonding groups coming off of it. One here, and then a double bond is treated as 1 bonding group. And again, if you don't remember that, that's from chapter 9 in this book on molecular geometry. So this central carbon here, it's kind of buried, is AX3. And then again, this carbon here was AX4 again. So you go, why do I need to know that? Well, you can see this is tetrahedral here, this is tetrahedral here, and then the carbon in the middle, it's AX3, it's sp2 hybridization. Because if it's trigonal planar, that's the hybridization. That's how this works, okay? And so therefore, this is trigonal planar, and that's so based on chapter 9 and chapter 10, you should be able to take definitely the Lewis structure and be able to give me a 3-dimensional structure of it. So this next form of compounds, this is an aromatic benzene ring here. And so again, it has delocalized electrons, which means these electrons can flow in the pi bond above the ring structure or below the ring structure. When we attach this functional group, this methyl group as it's called, methyl, and you say that looks like methane. Yeah, it would be methane if it had another hydrogen here, but we're using this bond, and so we call this a methyl group, all right? So a methyl group attached to a benzene ring is called toluene. And again, this is an aromatic compound. And then the last one here, we knock off a hydrogen. Instead of hydrogen, we put NH2 here, and that's called an amine. So amine is derived from ammonia, and you know ammonia is NH3. But what happens if I knock off a hydrogen, and now I have a bond here? That's the bond that's going to be created here, and these are called amines. And you're going to hear about, if you're taking any biology, you're definitely hearing words like acetone and methylamine. They're very common in biology. So here we go. Here's some naming. I want you to memorize it. The best way to name this is make you some flashcards. There is a program called Anki, and if you really want to know about it, just email me and I'll send you something about it. But it's free. You can put it on your cell phone. You plug in. You put in your what you're trying to learn. It's like electronic flashcards. Like you put methyl on one side and the formula on the other, and you cycle through them until you get the names down. And the ones that you miss more, it shows up more on your quiz or whatever until you get it down. The things you're getting correctly, it doesn't show up as much. It's a great way, electronic flashcards, to kind of help you memorize these different structures. All right, so here we have methyl, ethyl, propyl, isopropyl, which is, notice what isopropyl is. The bond is coming off of the central carbon versus the end or terminal carbon. So terminal carbon is propyl, and it doesn't matter which end this terminal part's coming off, it's still propyl. So it doesn't matter if it's on this end or this end. If it's on this end over here, this becomes the 3 and this becomes the 2, right? So it doesn't matter that way. But isopropyl, the bond's coming off the central carbon. That's why they're showing this in parentheses. They're saying, hey, this is the central carbon, and there's a methyl group attached to to this carbon on either side of it, so it looks like this. All right. Whereas up here they don't use the parenthesis because it is just a straight chain here. And you go, I don't know these names, methyl, ethyl, propyl. That's in chapter 2, so you may want to go back and look at naming in chapter 2 of some, at least the first 10. It's the first 10 carbon carbon chain compounds, like it goes methyl, ethyl, propyl, butyl. If you're doing it in chapter 2, we're just actually doing hydrocarbons, so it's methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. And then if we knock off one of the hydrogens and we have a bond here instead, it's methyl, ethyl, propyl, so forth. So these are called alkyl groups. Make sure you can speak the language here. These are called alkyl groups. Carbon, hydrogen based groups that we will bond to a carbon chain. So they show some more here on the next side. So there's the butyl we talked about, 4 carbons. And so we have butyl, again, straight chain carbons, and then we have tert butyl. And you do need to know tert butyl comes up a lot. You have the 4 carbons, so that's why it's butyl, and off of the central carbon is the bond. So off of that, so you got 1, 2, 3 carbons coming off of that. So right now, this could be a tertiary carbon. That's what the tert stands for, tertiary carbon, because there's 3 carbons coming off the central carbon. Then we have pentyl, and then we have isopentyl. All right, and you say, okay, I see this is coming off here, and I have the bond here, and you say, could I have this over here? You could, and it would still be the same thing. You could flip it around, it'd be the same thing, right? So isopentyl. Main thing there is you're getting out of this is isopentyl. So what I'm saying again here is, what if the CH3 is on this end, the CH2 is on this end? It'd be the same thing, but this is the way we'd write it, okay? So isopentyl, pentyl tells you it's 5 carbons, 1, 2, 3. Off this carbon here, you have this carbon and two of these things coming off. So that's what you see right here, right? You see that 1 hydrogen here, and then bam, bam, bam. There's my CH3, there's my CH3, and then there's my CH2. If it's going a little fast, just slow down, stop, and think about it. Think about what you're looking at here. So hexyl, we're just trying to get you to learn about the carbons. 1, 2, 3, 4, 5, 6. Again, I would go back to chapter 2. There's a whole table on just the first 10 alkanes. Again, these are called alkyl groups because we've knocked off a hydrogen. Now we have a bond here. It's an alkyl group. Sometimes designated by a capital R. Like if it doesn't matter what the alkane is, and I'm more interested in the structure over on this side, I'll just say R here. And then R you can substitute in hexyl, heptyl, whatever. So that's what this is doing here. And you're right, these can get branched, but again, that's beyond the scope of this class for right now. You'll get into that in organic chemistry. What I'll say about organic chemistry is that if you've struggled with the math in Gen Chem 2, you may really like organic chemistry. I see people who've struggled through Gen Chem 2, which to me is for engineers. For it is for chemists too, but it's taking phenomena that we see and then figure out mathematically how we explain that phenomena. Here we're looking at structure. We're looking at the building block of carbon and all the compounds that we can make from it, and then investigating the properties of that substance. So here are the functional groups that I do want you to know, because this is what really starts to change basic chain structures of carbon. And so what we have is, these are called, this is the hydroxy group, all right, hydroxy group. And when you attach that to any carbon group, the alkyl group, so again, it could be CH3, it could be CH3, CH2, and then the bond. So that's the alkyl group, that's R. This would, if it's attached to CH3, it's methanol. If it attaches to CH3, CH2, it's ethanol, and so forth. So that's why you have to know the chain names: methyl, ethyl, propyl, butyl, and then we attach it to this, and then it becomes an alcohol. Our carboxylic acid, we've seen this before. It's got that carbon. It's bonded to a hydroxy group and double bonded to an oxygen like so. That's called a carboxy group. It's what gives us things like acetic acid, propanoic acid, and so forth, butanoic and so forth. Then we have an ester, and so what I like to do here is an ester and a carboxylic acid are very closely related. All we're doing is knocking off this hydrogen and putting on another alkyl group. All right. So it looks like a carboxylic acid, but we don't have the hydrogen anymore. We have another alkyl group. You go, why do I need to know this? It is the esters that give you things like the smell of a banana, spearmint, and things like that. Combinations of carboxylic acids, esters, aldehydes, and ketones is pretty much what makes up most of your scents and perfumes and flowers and things like that. So esters are important. They are generally something that attracts us to the smell or makes us think about something with smell. The thing to remember, though, a lot of these compounds in small amounts, maybe not so toxic, but in large amounts can be very toxic. So keep that in mind. An aldehyde we've talked about before. The hallmark is you see that you first focus on the carbon double bonded to the oxygen. You'll have a group over here that's attached, but the key is that one of the bonds coming off the carbon double bonded oxygen is always a hydrogen, and that's called an aldehyde. It's called a carbonyl group. If we knock the hydrogen off and put another alkyl group on here, now it's still a carbonyl group, but it's called a ketone. Okay. And then the last one we've talked about before, it starts out as ammonia. We knock off one of the hydrogens. Now we have a bond here, and so it's called an amino group. This is called a primary amine. It's only so we have one attachment there to the alkyl group, primary amine. All right, so let's look at a secondary amine. We knock off another hydrogen. And so we have now, this is going to attach to whatever, but then we have an alkyl group here instead of a hydrogen, and that's called a secondary amine. If we knock off the last hydrogen here, where we have two alkyl groups coming off the same nitrogen, that's called a tertiary amine. Just like the carbons, we saw that whether a carbon's single bond, bonded to one other carbon, two carbons, or three carbons. Same thing here. Now, I find students mix up amines and amides. They think they're the same thing. There's a difference, though. An amine, always remember, it's derived from ammonia. An amide is where we have a double bond, we have the carbon double bonded to an oxygen, and then the amine group attached to it. You have to have both of those. And when we have that, it's now called an amide. Okay? You go, why do I need to know this? You've heard of peptides, you've heard of proteins, you've heard of that's what I think of, peptides and proteins. All right. So again, you can have a primary amide. You can knock off this hydrogen here. Now it becomes a secondary amide. You can knock off both hydrogens off the nitrogen. It becomes a tertiary amide. So make sure you can distinguish between amides and amines. Really important. They are not the same thing, and they have different chemical properties. So let's talk about classes of organic compounds. So Again, when we have an alkyl group attached to the hydroxy group, we have alcohols. And so you look at the alkyl group here, this is the methyl group. It's attached to the OH here, the hydroxy group, and we call that methanol. So that's why you have to know at least the first 10 in this class, you know, methyl, ethyl, propyl, and so forth, up to decyl. So make sure you know those from chapter 2. So what you're probably more familiar with is ethanol. So ethanol, again, what's the hallmarks? The functional group here is the hydroxy group, and then the rest of this is the alkyl group. In this case, the alkyl group is ethyl. So this is ethyl alcohol or ethanol, both of those names, ethyl alcohol or ethanol. Also called dog, because maybe you've heard it called dog, but you know, you could rotate these. This can rotate, and so you can have something that looks like that's the legs coming off the other carbon, and then you'd have the two legs down here, and then you have the OH group, the hydroxy group, coming off as the head. So that's why they call ethanol dog sometimes. Then we have isopropyl alcohol. You probably have some in your medicine cabinet. Again, you have to know the alkyl group, and there we have the 3 carbons, so that's propyl, but the bond is coming off the central carbon and not the end carbon. So if it's the end carbons, if the OH was coming off here and there's a hydrogen here instead, then it'd just be propyl alcohol. But because it's coming off the central carbon, and now we have the functional group hydroxy coming off that carbon, it's called isopropyl alcohol. But notice everything we've done here, everything that has a hydroxy coming off of the carbon and the straight chain carbon here, it's in the classification of alcohols. Now, from this, we can look at hybridization. And so, again, if hybridization is totally new to you, what I would tell you to do is go back to chapter 11. Let me point that out, what page that's on in your book, so you can, and this is the Burge book, just to reference this. So, in chapter 11, it is section, let's see. Let's see if I can find it real quickly. Maybe it's in chapter 9. Let's go back and see if it's that. Maybe I've been referencing that wrong. I'll have to go back and look. Yeah, it's actually chapter 9, section 9.4, and it's on page, it starts on page 385 in the Burge book, and it goes through page, well, if you want to see it all, you go back and look at page, up to page 400, all right? So here's what I want you to get out of this. This hydroxy group, what this is, just think about it, it's really water, right? Instead of having a hydrogen here, that's where the bond is, and then you got a lone pair of electrons here and a lone pair of electrons here. And so in classification terms, this is AX2E2, and that's one of the bonds here. And so it's 4 things coming off the central atom. If it's 4 things coming off the central atom, the hybridization is sp3. All right? When you look at this carbon here, we don't need to reinvent the wheel for this part. It's the same as here. But if you look at the carbon here, this carbon is AX3. It's got 3 bonding groups coming off of 1, 2, and 3. And so if it's 3 things coming off the central atom, the hybridization is sp2. All right, and so we can see this clear here. This again, AX3, 3 things coming off the central atom. The hybridization is sp2. All right, and then with the amino group, you got nitrogen here. You've got, let's think about what this looks like. Ammonia started out looks like this, with a lone pair here. If we knock this out so it can bond with something, now we have the amino group. So you still have 4 things coming off the central atom. And so if 4 things are coming off the central atom, it's AX4. So it's still AX4 here. Or AX3, let's do it this way, AX3E. And so 3 bond, 1 and this one and this one. And then the lone pair there. So 4 things coming off the central atom, sp3. So again here we can see it's sp3, and then on this carbon here with the amide group it's sp2. So let me just reference this, let me go back and reference, since I guess I said it incorrectly before. The table that you want to look at is table, to get this down, and again I'm assuming at this point you can do Lewis structures and you can do geometries, but maybe not the table 9.4 on page 391 is where they show the relationship between the classifications and the hybridizations. So how do we name these compounds? What's the process? So again, you have to know the first 10 carbons. And so what we look at, it's meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. All right? And then we have prefixes for the halogen substitutes. So we're going to substitute either fluoro, bromo, chloro, or iodo. And the reason why we use these, they're not ions, right? They're not fluoride, chloride, bromide, iodide. These are covalently bounded to the carbon. So we use words like fluoro. And that tells us that, hey, we're not talking about an ionic compound here. We're talking about a covalently bounded compound. So alkanes are the straight chain carbons, and we're talking about just single bonds between the carbons. So it says to name a substituted alkane. That means we've taken off a hydrogen. We're going to place a substituent onto it. That substituent is what gives that chain its chemical and physical properties. And so fluoromethane and fluoroethane and fluoropropane are going to have different chemical and physical properties. So the first thing you have to do is identify the longest continuous carbon chain. Make sure you take the time to do this, because carbon can start looking like this as a line where every one of these points here is a carbon, but we don't draw those. And if you don't get the right number of carbons in the chain, then you're going to get the whole name wrong. So on this one here, we would have 6 carbons, so this would be hexane, right? 6 carbons, hexane. Make sure you spend the time to determine. And where it gets tricky is like, what happens if I have a carbon here, and I have a carbon here, and I have a carbon here. Well, now you got 1, 2, 3, 4, 5, 6, 7. The longest chain is through here, and this is going to be a group, an alkyl group coming off of this longer chain. So that's where it gets tricky. Take your pencil and draw the longest continuous chain. Take the time to do that so that you identify that correctly. It's got to be the longest continuous chain. Then you number the carbons in the continuous chain beginning at the end closest to the substituent. So like on this one, let's see, have I really messed this one up? Let's say there's a carbon here and a carbon here. So 1, 2, 3, 4, 5, 6, 7, 8. So this is octane if I go all the way out to here. So if I start here and I go 1, 2, 3, 4, this ethyl group is off of carbon number 4. If I number this one 1, 2, 3, 4, 5, that's not good because this is a higher number. So I would number from here, but you've got to, sometimes you do work from the other end. So be careful wherever the alkyl group or substituent is coming off, that's got to have the lowest carbon number here. Lowest carbon number. And if it's not, you've made a mistake. Then it says identify the substituent and use a number followed by a dash and a prefix to specify its location and identity respectively. Okay? So let's look at that. Let's look at an example for that. I like this example. So the first thing is identify the longest carbon chain. So this is 1, 2, 3, 4, 5. And then it's 1, 2, 3, 4, 5. Okay. So the chain is the longest, continuous line 1, 2, 3, 4, 5, or you could go 1, 2, 3, 4, 5. So it's 5 carbons long. The base chain is a pentane, right? The base chain is a pentane. 5 carbons. So do that first. And that's how I do it. I keep the pencil down and draw through it. And that way I've identified it and no problem. All right, the next step is, if it really doesn't matter which way you identify the longest chain is, I would do it this way since it's easier. So if this is the case, this is an alkyl group, this is a methyl group, and we want this attached to the lowest numbered carbon. So we would number this carbon 1, this one 2, this one 3, this one 4, this one 5. You would not number this carbon 1 and this 2 and this 3 and this 4 because that's a higher number than 2 here. So you don't do that. Always number your carbon chain with the lowest number where the constituent or substituent is coming off of. In this case, this methyl group. So that's what they show on this slide, and that's what you see: 1, 2, 3, 4, 5. Lowest chain here, lowest number here. Okay, identify what this is. You have to identify that this is a methyl group. It's 1 carbon. You can think of methane, but instead of a hydrogen being here, it's a bond to the next carbon here. So it's a methyl group. So we're going to put this all together. We're going to name it. So it's pentane, it's methylpentane, and it's on the second carbon. So there's our name, 2-methylpentane. 2 tells us which carbon it is on. 1, 2, 3, 4, 5. It's on the second carbon. Methyl group is the alkyl group attached, or the substituent in general. And that alkyl group is called the methyl group. So methyl, and then the chain is 5 carbons long, pentane. So 2-methylpentane, we just say 2-methylpentane. We don't say the dash, but the dash has to be there to separate the number from the name there. 2-methylpentane. Let's go back. I want to show you something. I think this throws students off too. Let's go back to this one here. Notice it doesn't matter which one of these that you choose. They're both going to be the same thing. If you choose this one, you're going to say this is carbon 1, this is 2, this is 3, this is 4, this is 5. Again, it's on the second carbon. There's my methyl group, 2-methylpentane. It's the same thing, 2-methylpentane. So, some people don't like that about organic. There's, it looks different, but when you really get down to it, it is the same thing. We will look at isomers here in a minute, which those are a little different. All right, so give the names for the following compounds. All right, so the first thing you're going to go is you're going to say, okay, this is in a class of compounds called alkanes. Alkanes are carbon-based compounds that are single bonded. All right. This is called so what we want to do is we got an alkane here, and it's an aliphatic hydrocarbon if you want to think of that. And so we put our pencil down. We go 1, 2, 3, 4, 5. That's the length of the carbon chain. So if it's 5 carbons long, we know it's pentane. And then we start to number the carbons. So we can say 1, 2, 3, or if we did it in reverse, this would still be the third carbon. So 3 is the lowest number we can get where the substituent chloro is attached. So we would label this as 3, and then put your dash there, say chloropentane. All right, 3-chloropentane. It's pretty easy. I think you're going to, this chapter, I mean, it should seem easier than stuff we've covered, and that's okay. It's fine. The only thing about this chapter is Lewis structures, molecular geometries, hybridization. So let me write down some of this. This is what you have to do in order to be successful. In chapter 2, you have to know your hydrocarbons, all right? Methane, propane, butane, up to decane. Carbons 1 through 10. All right, in chapter 9, or chapter 8, you have to be able to do Lewis structures. Chapter 9, you have to be able to do geometries, and you have to be able to do hybridization. Okay. And then we've got this in chapter 23. So, okay, we got this compound. So this is what I see students do. They go, oh, my carbon. They always look this way for their longest chain. 1, 2, 3, 4, 5. Is that my longest chain? What if I went 1, 2, 3, 4, 5? Is that my longest chain? All right, let's erase these. And let's go with something different here. What if I go 1, 2, 3, 4, 5, 6, 7? Oops, 7. All right, so 7's the longest. So knowing that it's 7, you know it's heptane. And you go, how do I know it's heptane? Because you looked at this part in chapter 2. All right? It's heptane, 7 carbons. Then you look for substituents. So if that's my chain, this is coming off of the chain. And you go, oh yeah, that's a methyl group. So identify the substituents. Could be a chlorofluorobromo. This could be an alkyl group, methyl, ethyl, propyl, butyl, so forth. All right, so now that we've identified the substituent, we want to number this so that it has the lowest number for this carbon right here. So 1, 2, 3, 4, or 1, 2, 3, 4, it doesn't matter. Doesn't matter which way we number the carbons. Both ways it comes out that the carbon in the chain is number 4. So now we can put it all together, right? 4-methyl heptane. 4-methyl heptane, or just 4-heptane. Is the way we would speak it. Okay. Don't let Chem 180 just be totally killing you for not being a chemist or want to go this route. The organic is so rewarding. There's so much you can do. I mean, just think about it. Oils, plastics, polymers, pharmaceuticals, just so much in organic chemistry. Environmental chemistry, atmospheric chemistry. I mean, it just goes on. And this is the stuff you do. Is you're going to look at how do you make this compound? How do you make something new and classify it and break it down so you know what the structure looks like? What are the chemical and physical properties of the compound? Where could you use this in material science to make a new material? I mean, it's just neat stuff here. It really is. Organic is just, I mean, it's its own chemistry. It's so interesting. All right, let's look at another example. I hope you're enjoying these. I hope you feel like this is a respite from all the math we've done this semester. All right, so let's look at this one. Well, you can see the longest chain is straight across here. Doesn't matter if you went up or down, it'd still be the same number of carbons. So I agree, if you got a choice, you're going to go with the straight line here, not bend up. But okay, so we got 1, 2, 3, 4, 5, 6 carbons long. We know that's hexane. All right. We identify the substituent. It's an alkyl group called the methyl group. And then the only problem I see students make a mistake is this is going to be carbon number 2, right? I don't know what they're doing here. Look at this. This isn't, there's a typo here. So let's just do this one, then we'll do this one down here. So, you know, if you label this as carbon number 1, this would be 1, 2, 3, 4, 5. And you go 5-methyl hexane, and you go, no, there's no way that's right. Because you can label it this way and say 2-methyl hexane. And that would be the correct name for that one. This one down here, it's 7 carbons long. All right. And it doesn't matter which way you number them. This is going to be the 4th carbon. And so this would be 4 dash, and again, what's the constituent? It's an alkyl group, 4-methyl, 4-methyl heptane. All right. Not bad. All right, so now we're going to get into something a little more complicated, because in reality, things aren't all straight chain. So we're looking at this. It says naming organic compounds in molecules that contain 2 or more identical substituents. The prefixes di, tri, tetra, penta, and so forth are used. And those are actually in chapter 2 as well. Let me see if I can find that real quickly and reference that for you. So in the Burge book in chapter 2, they have a table of prefixes. And those prefixes are on, let me see here. They're on page 62. And they're in table 2.4. So if you don't know, mono, di, tri, so forth. We don't use mono. We just start at di. So di, tri, tetra, and penta, and so forth. All right, so let's say we're going to name this compound. The first thing you have to do is find the longest chain. So if I go this way, it's 1, 2, 3, 4, 5. If I go this way, it's 1, 2, 3, 4, 5. And so that's the ones that's going to give me the longest chain. And it doesn't really matter which way I do it there. So we're just going to go with the straight line because they're both the same longest chain. Okay. So now what happens is we identify the substituents coming off of that chain. We've got a methyl group here, and we have a methyl group here. And so if you number this carbon as 1, this would be 2, this would be 3, this would be 4, this would be 5. That doesn't give us the lowest numbers for these 2 groups. So it's best to label this one as 1, this one as 2, this one as 3, this one is 4, and this one is 5. So don't label the carbons that way. So take the time to do that. I find that's where students first make a mistake here, is they're not getting your lowest numbers, and it's because they're just, you got to think about what's coming off of here. So in this case, this methyl group's coming off carbon 2, and this one's coming off carbon 3, And so we say 2, comma 3, and there's your dash again. Di stands for 2, and then the functional groups are both methyl, so that's how we can say that, dimethyl, and the longest chain is pentane. So 2,3-dimethyl pentane. All right, this is an important slide because this is what happens when you have some things that happen that just make it a little more challenging. It says, in the case when two or more different substituents are present, the substituent names are alphabetized in the systematic name of the compound. So that means the lower, like between ethyl and methyl, ethyl is going to come first because ethyl east comes before M. The numbers are used to indicate the positions of the alphabetized substituents. Same as before. You got to say which carbon is the ethyl group coming off of, which group is the methyl group coming off of. If a prefix is used to denote two or more identical substituents, the prefix is not used to determine alphabetization. Alphabetization, which is you don't say diethyl or dimethyl takes precedence over ethyl. All right. So even though it's dimethyl, methyl starts with an M, ethyl starts with an E. Ethyl should have come first. Ethyl should come first. You may want to stop and think about this. This is an important slide. I see a lot of students make mistakes based off what's on this slide here. All right, let's put it to practice. So notice the things are getting a lot more complicated. And so the first thing is make sure you get the right number of carbons. And they're being nice to you, right? 1, 2, 3, 4. I mean, you could go two ways here, but they're being nice. They're putting they're making it so your longest carbon. And maybe that's what happens is people get kind of always thinking that this is going to be the longest chain. And it should be. If you're writing it down, you shouldn't try to make it the other way. So you do typically make the longest chain along the horizontal line to make it easier for everybody. All right, so we have an ethyl group here, and we have a methyl group here. Now you say, well, why didn't you label this one 1, 2, 3, 4, 5? Well, I get larger numbers, right? I get larger numbers here. So we definitely want to label the numbers like we have already. And so then the ethyl group is here. It's an alkyl group, 2 carbons long, ethyl, and we got a methyl group here. And what we mean by alphabetized, the ethyl comes before the methyl. So we say 4-ethyl, carbon 4, -ethyl, the alkyl group. And then we say -2, second carbon, methyl group. And then the long chain, the backbone of this structure is a hexane. So 4-ethyl, 2-methyl, hexane. All right, so then let's look at this one. Again, the longest chain is 6 carbons. Okay. And so, again, this numbering system gives us the lowest overall. So this ethyl is still on the 4th carbon, so 4-ethyl. Ethyl takes precedent over methyl, even though this is di. Again, you go back to the original alkyl group, it's methyl. It's not the prefix. And so this is 4-ethyl, 2, 2, because you got 2 methyl groups coming off the same carbon. Okay. That would be a tertiary. This would be a tertiary carbon, right? Tertiary. It's attached to all of the carbons. So 4-ethyl, 2,2-dimethylhexane. And the way you get good at this is by doing lots of problems. So you got your homework, but you may want to try some of those in the back of the book as well, so that you can get plenty of practice in naming. This naming's not hard. It's just got these rules, and you have to know some of prior knowledge to do it, but I think you'll find this is much easier than what we've been covering. All right, I'm going to stop this video here because we're going to get into some more functional groups, and we've got about an hour video. It's pretty long, so we'll stop here and we'll pick up on the next video after this.